In our last video, we talked about Thomas Young's double-slit experiment, and specifically how the interference pattern that emerged from that was definitive proof that light actually travels through space as a wave. And this has allowed us to now talk about one final topic on this unit on light and optics, which is that of physical optics, otherwise known as wave optics. In other words, phenomena that can only be explained if we treat light like a wave, or like we're treating it in its proper physical fashion. In particular, we're going to look at two phenomena: thin film interference and polarization. So let's start with something you've definitely seen before, which is just a bubble. And something that you've probably thought about or noticed at some point in time is that bubbles have very, very distinct colors. Specifically, if I'm going to go ahead and focus in on here, we kind of see these regions. Now, granted, the majority of the bubble is transparent. We're seeing what is behind the bubble, but there's a lot of regions that are at least tinted, if not completely opaque. And we're seeing some red, blue, and green, but we're even seeing magenta, yellow, and cyan. And the question is, why are we seeing these specific colors, and why are we seeing them at all? And this really comes down to the structure of the bubble itself. Really what it is made out of and what is inside and outside of it. So specifically, we have air both inside and outside the bubble, but then the layer of the bubble itself is this really thin film of soap and water, this really, really thin surface. So let's zoom in on this piece of the bubble here, this side piece. And we've got air on the outside, air on the inside. Air has an index of refraction of 1. And this thin film of soapy water, we don't know its exact index of refraction, but it's definitely greater than 1. And when we say a thin film, we're talking about something that's on the scale of nanometers to micrometers. So that's times 10 to the minus 9 meters to, at its biggest, times 10 to the minus 6 meters. So extremely, extremely, extremely thin. And when we're looking at this, okay, so let's talk about what's going to happen here. We have light that is incident on the outside of the bubble, traveling from somewhere. And when it hits the bubble, some of it on this outer boundary is going to reflect from there, off the soapy water, and just travel back in the opposite direction. But some of the light is going to move through the soapy water because it is a transparent material. So some of it is going to be transmitted in. Now, quick note, it would be bent because it would be refracted. Now, I went ahead and tried to make this as direct as possible to minimize that effect, just as we talk about it here. But some of this light is going to be transmitted through the bubble. And when it gets to the inside of this layer, it's going to encounter air on the other side of the soapy water. Well, when that happens, once again, we have some light that reflects back from this inner layer, this inner boundary, and some of it which is transmitted beyond that point through to the other side of the bubble. Well, then what's going to happen now is this light that's been reflected back from the inner boundary is going to escape and get transmitted back out of the bubble in the direction that it came. Well, what we end up having here, though, is we had light that was reflected from this outer boundary and light that was transmitted through the soapy water, reflected from the inner boundary and transmitted back, and that is going to actually end up interfering with each other, these two different light waves. And in this particular situation, with the way I drew them in such a way that they were out of phase with each other, and that would result in destructive interference. So those light waves would actually greatly diminish in their brightness. If I had drawn it differently, it might have been constructive interference, which would have greatly amplified their brightness. And this process, this natural phenomena, is known as thin film interference. And let's briefly go through the details one more time. It's a natural phenomenon that occurs when light is incident on a thin film of transparent material. And this thin film in this particular case was soapy water. So light is incident in, it's coming in, and it's hitting this thin film. And what's going to happen is some light reflects from this first boundary, so it's going to basically reflect straight backwards. That was what's showing right here. Some of it is transmitted through the material and then reflects from the inner boundary and gets transmitted back out. And what's going to happen is that these two reflections, the one from the outer boundary and the one from the inner boundary that was transmitted through, well, they're going to interfere with each other. And they could either interfere constructively or destructively. And what are the factors that affect this thin film interference? Well, there's quite a few. First, what is the wavelength of the light? Because if I've got a different wavelength, that could mean that when the waves come out of this bubble or this thin film, they could be in phase or out of phase. It all depends. There's that. One big one is the thickness of this film. If the film is just a little bit thicker or a little bit smaller, that means I'm going to have a little more wavelengths or a little fewer wavelengths going through the basically thin film itself, and that could change whether they're in or out of phase. The index of refraction of these materials matter because what actually happens is when we have the light going from air to soapy water, so that's going from a lower index of refraction to a higher index of refraction, that's actually going to reflect in such a way that's going to reflect out of phase, as though it hit a hard barrier. And at the same time, if it goes from soapy water to air, which is from a higher index of refraction to a lower index of refraction, it's actually going to reflect in phase because it's kind of a softer barrier. So basically, if these index of refractions are greater or less, that can change whether or not the light waves flip or not when they encounter these barriers. And lastly, the angle. Right here I showed this fairly direct on, but if this light is coming in at a greater angle, that could change how many wavelengths of light could go through this material before it hits the inner boundary and then comes back out. So there are many, many different factors there, but the really key point is that for this to occur, light must behave like a wave. Thin film interference is not possible if light behaves like a ray, because interference, which occurs when we've got two waves occupying the same space at the same time, well, it requires waves because they have to occupy the same space at the same time. If you've got particles, they cannot do that. So let's return to this picture of the bubble for just a second. Well, we had these blue, red, and green regions. And why exactly are we seeing those? Well, that's largely because those are results of constructive interference. Some of the white light that is going into the bubble, some of it reflects off the outside of it, some of it goes through the bubble itself to that inner boundary, reflects from the inside, and when it comes back out, they basically is just wide enough and it's just at the right angle and the wavelength of light is just right that in this region, for instance, we have green light constructively interfering with green light, which makes it brighter. Here we're getting blue light constructively interfering with blue light, which makes it brighter. And here we have red light constructively interfering with red light, making it brighter. What about the other colors? Well, these are actually all a result of destructive interference. Remember that when we don't have any red light, well, what are we going to have left? So basically what's happening here is that the red light is going in and is then reflecting off the outer and inner barriers, and it's destructively interfering with itself. And if we remove red light from white light, we're left with blue and green, which makes a cyan color. If I have blue destructively interfering with itself, well, then I'm left with red and green, which leaves me with a yellow color. And if I have a green destructively interfering with itself, then I'm left with red and blue, which leaves me with a magenta color. Additionally, we should note that a lot of this seems to be fairly transparent, because what would be happening here is, remember, some of that light was able to go from one side of the bubble to the other without encountering any of this interference. But that's explaining why we are getting these bizarre color patterns. Alright, now we're going to make a big shift to a completely different natural phenomena that also requires physical or wave optics in order to be properly explained. So what I have right here is a picture of a light wave. Remember, that's an electromagnetic wave where this is my electric field. Perpendicular to this electric field is the magnetic field, but the light wave is actually being transmitted in this third dimension in this direction at the speed of light, c. Now, we didn't talk about this previously, but this right here, the direction that the electric field is oscillating, which in this particular diagram is up and down, is known as the plane of polarization. It's the plane in which the electric field of the electromagnetic wave oscillates. So here, this would be, for instance, the plane that's basically the plane of your screen. This electric field is basically going up and down on your screen. Well, if we were to rotate this light wave just a little bit, well, the plane of polarization would also rotate with that electric field. So I've rotated it so that the electric field kind of goes into the screen, and that's caused the plane of polarization to also go into the screen for the part that is closer to the top of your screen. So let's look at this nice snowy expanse here. And the first thing we want to know is, okay, let's talk about light coming from the sun. When light comes from the sun, it is largely unpolarized. And what that means is that the waves have all different planes of polarization. One light wave is going to have a plane of polarization going this way. Another one will be going that way. One will be going straight up. One will be going horizontal. They're all going to be going in these different directions. Now, that is typically, I said for the sun, but really this is typical for any source. So if you have a light bulb, you have a candle, you have the sun, it's going to be emitting unpolarized light where all of it is going in different directions. But the thing is, though, is that when the light hits the snow here, it's largely going to become polarized. And by polarized, we mean all the waves have the same plane of polarization. So when you hear that word polarized, it means they're all going in the same direction. And really, how do I know that's going to happen here? Well, that's actually because typically, when we have something reflecting from a flat surface, what is going to occur is that all the light waves are going to basically be reflected in such a way that their plane of polarization matches that surface. So if I had a horizontal surface and unpolarized light came in, all the light that's reflected would have a horizontal plane of polarization. If I have a vertical wall, all of the light that's reflected will have largely a vertical plane of polarization. Here we have kind of this slant here, so the light has this slanted plane of polarization. And a quick note, not all of this light rotates to this plane. What would happen is, for instance, this one that was already in the plane would just be reflected, and then some of these which are partially in this plane, some of the light would be reflected and some of it would be absorbed, but the part that's reflected is largely the part that's in this plane. If you had one going completely in the opposite direction, it would probably be absorbed. Well, is there another way that you can polarize light? And there actually is, and one that you're very, very familiar with, and that is with something known as a polarizing filter, which a lot of sunglasses contain. So a polarizing filter is ultimately a piece of plastic, which on sunglasses could be like a film over the glass, but a lot of times it is literally going to be a concrete piece of plastic. And what it has in this piece of plastic is these long chains of molecules. That's actually what I'm showing you here. I have a filter here, and these black lines are long chains of molecules called polymers. And what occurs is that any light waves that are in the same direction, their plane of polarization, I mean, in the same direction as these polymers, well, they're going to be absorbed by them. So the only light that goes through this filter is the light that is not absorbed by these polymers. So if I have unpolarized light here, it encounters this filter, and because these polymers are oriented in the horizontal direction, we result with vertically polarized light. So this would actually be called a vertical polarizing filter because it is taking unpolarized light and resulting in vertical polarized light. Now the thing is, though, is I could actually take this filter and I could rotate it 90 degrees so that its polymers were going straight up and down, and what would happen is we would result in horizontally polarized light, so there would therefore at that moment be a horizontally polarized filter. So its orientation does in fact matter. But what is this going to do is that, well, it means that we've got a lot of light coming in, but only some light can actually go through the filter, which greatly reduces the intensity or the brightness of this light. So for instance, if I'm looking at the surface of this water here, and in this right here, let's say this picture was taken probably without any filter on it at all, and you see you get a lot of glare here, but if we add a polarizing filter to it, it cuts out a lot of that glare because it's removed a lot of that, in this case, horizontally polarized light, because that is the light that is coming off that surface, which therefore reduces the intensity, but it can also make it much, much easier to see. But once again, what's really key here is that this also requires wave-like behavior. If the light was not traveling in a transverse wave-like fashion, it would just go straight through the filter. The filter only absorbs light that is oscillating in the same direction as the direction of these polymers. If light wasn't a wave, it could not be polarized. So what are our final takeaways on this video on physical optics, otherwise known as wave optics? Well, one, can we explain how thin film interference occurs? Can we identify factors that affect it, particularly resulting in either constructive or destructive interference? And can we describe what we would actually observe if we were seeing it occurring in some particular situation? Can we describe how unpolarized light and polarized light differ from each other and explain how we could polarize light that is unpolarized? And lastly, can we explain why the wave model of light is necessary to explain both of these specific phenomena, and why the ray model of light is in fact insufficient?